So hello and welcome back. So in this video, basically based on what we have in the book, we are supposed to talk about the limits of trigonometric functions. But there are a couple of things here that need to be understood before we can get to the limits of trigonometric functions. And what that is basically the idea of basically functions. First, you need to understand what a function is, and there are a couple of things basically like the real valued functions and the real functions and things like that. And then based on that you can understand, because the whole idea of calculus, and basically the whole idea of calculus and derivatives, and then with that also comes limits as well. This whole idea is based on functions. And then there are basically loosely there are basically two types of course there are many types of functions, but loosely there are, what is relevant here is called, there is some type of function which is called real functions, and there is something else called real valued functions. So what you want to do here is, first of all, basically we need to know what functions are. So once you know what a function is and where it actually comes from, then we will basically talk about real functions and real valued functions, and then we will go back to the rest of our discussion, which is basically the limit of real valued functions and trigonometric functions. Perhaps we should have done this a little bit earlier, although over there it was really not very necessary, but over here this needs to be clarified. We can move any further. So basically what the function is, and this is basically the chapter 2 of this is basically chapter 2 of class 11. And I'm taking some material from here to cover basically what the function is. This is from the same set of books. This is chapter 2 of class 11 mathematics. And that's basically what we want to do here. And this is basically what you do. You normally need in a university course or whatever sort of course you might need, but the basics of your work is always calculus, and then of course the basics of calculus is always functions. So basically the whole idea of a function is some sort of relation between two objects, you could say. For example, we come in our daily lives between people, there are basically all of these relations, like for example brother and sister, or father and son, teacher and student, and that sort of thing. So this is basically some sort of relation that we can find in our daily lives between two people, for example. In mathematics, there is also something called there is different kinds of relations. For example, the number m is less than number n. For example, you can say that m is less than n. Or for example, the line m, for example, is parallel to the line n, for example. Assuming that these two are two lines, for example. Or you can say that, for example, the set A is a subset of the set B. And so in all of these cases, and of course there is probably an innumerable number of relations between different objects that you can find in mathematics, and in all of these cases we notice that a relation basically involves pairs of objects, involves basically pairs of objects in a certain order. That is of course not a relation but a relation involves pairs of objects in a certain order. Now what we really are doing here, we are basically learning how to link pairs of objects, how to link pairs of objects from two sets and then introduce relations between the two objects in the pair. And then introduce relations between the two objects, in the pair. So what that means is that, from basically this first part over here, how to link pairs of objects from two sets and then introduce relations between those two objects. For example, suppose that you have two sets. For example, you have 2, 3, 4, 5, and then you have, for example, 3, 4, 5, 6, 3, 4, 5, and 6. And a pair of objects from these two sets, for example, would be 2 and 3. 2 and 3. Over here you have basically, for example, 3 and 4. Over here you can have 4 and 5. Over here you could have 5 and 6. So these are basically pairs of objects from these two sets. You can call the first set, for example, you can call it set A. The second set you can call it set B. And then this would be a pair which has been taken from these two sets. So now sometimes it's possible to have some sort of relation between the two objects in the pair. For example, if I call all of these numbers, for example, x, and if I call all of these numbers, if I call them y, you can always see that x is equal to y minus 1. or basically you can always say that you can say that y is equal to x plus 1, or x plus 1 is always equal to 3, meaning that the number that you can find here, if you add 1 to it, you will get y over here. That's basically the relation that you can find between these numbers that you have taken from these two sets. So that's basically the relation that you can find between the two objects in the pair. And then for example, you can use some sort of specific notation. In this case, you can call this, for example, 2, 3 using this notation, 3, 4 using this notation, 4, 5 using this notation, 5, 6 using the same notation. And then we could probably also put all of these in a set and call it, for example, give it some name. Any name would do for at this point. For example, 2, 3, 3, 4, for example, 4, 5, and for example 5, 6. And since this is some relation between these objects in some specific order, I call it R, for example, having these basically a set of pairs that have been chosen from these two sets. And then you can do all kinds of different things using these numbers. Of course, you might already be familiar with all of them, but probably you haven't thought about them in this manner, because usually this kind of thing is not discussed usually this kind of thing is really not discussed in high school. You don't you don't really know, for example, where a polynomial comes from, or you don't really know, for example, where algebra comes from. You don't really know where variables come from. But all of a sudden, for example, when you're in doing high school or middle school, or a few classes higher than that, and so on and so forth, all of a sudden, for example, some concept is introduced, for example, called, for example, equations, or for example, quadratic equations. And then, of course, for example, these are in the form x squared plus 2x, for example, plus 3 is equal to 0, and then you're supposed to solve this equation. But then it's not, of course, easy to figure out that, for example, this equation is nothing but a polynomial of degree 2, for example. And we have talked about polynomials. We said that f of x, for example, would be equal to a of 0, for example, a of 1 times x plus a of 2 times x squared, plus all the way up to, for example, a of n, x raised to the power n. So now if here n is equal to 2, if here I said n is equal to 2, then I will get some second degree polynomial, which is of course called a quadratic equation. If you set that polynomial to 0, then that becomes a quadratic equation. And of course a polynomial in turn comes from basically comes from basically two algebraic terms. For example, if you have at least two algebraic terms that you have added together, that becomes a polynomial. So all of these things are really related to one another. So basically what I mean to say is that all of these concepts are just really related, and they are just connected together. So if you when you basically understand the relationship between all of these concepts, then of course you understand mathematics properly. So meaning that mathematics is not these disconnected islands to you. They are basically, for example, all of these different concepts in algebra, for example, they are all connected together under the name of the algebra, and then basically there is, for example, all of these other concepts called, for example, related to one another using, for example, geometry. All of these other concepts called geometry, for example, and then for example there is something called analytical geometry, analytical geometry, for example. And then, for example, these two are connected together using analytical geometry, and then there is all the other concepts again connected together in this way and in that way, and so on and so forth, and the whole thing basically becomes mathematics. So that way you can make sense of mathematics as a whole. Now so basically what we want to do now is that so basically one thing that we can do with these, what we want to do here is to link pairs of objects from two sets and then introduce relations between the two objects in the pair. And then the next thing that we will also do here is that we will learn about special relations. So these were some sort of, we could actually find some relations between these two objects in a pair, and there is some specific kind of relation. There is some specific, meaning that in this way that we found relations between, for example, one object from this set and one object from the other set, one object from here and one object from here. Of course, you can of course find as many sorts of relations between different objects from these two sets. Now, among all of these different kinds of relations, there is one specific kind of relation which is called a function, and that basically we want to talk about as well. And of course, you know that functions are actually one of the most important, I would say, one of the most important concepts in mathematics, because a function, what it does, as very well put here, a function, what it does, it captures the idea of, the idea of mathematically precise correspondence, precise correspondence between one quantity with the other, or between two quantities. So that's basically what the function does. It captures the idea of mathematically precise correspondence between two quantities. So that's basically what we want to do. That's basically what we want to do here. So let's get started with sets and the Cartesian products of sets, and then we will work our way through the whole of the rest of the material. Okay, so now basically the next concept that you need to understand here about functions. I hope that you're already familiar with the idea of sets. I don't really know how to define sets, and that must be I know that basically a set, for example, a set of numbers, I know that you could say that, for example, you can define a set, for example, I know that you can define a set, for example, you can say that the set of natural numbers, for example, the set of natural numbers, and of course I cannot really go that back there because it's back there in class, I don't know, 5, 6, 7 or so, and I mean it doesn't make any sense to go so back, I mean so back into class 6 or 7, but these ideas are simple to understand, and you usually don't need much definition for them. So for example, the set of natural numbers has been defined as for example, the set of all numbers starting with 1, and then you have 2, you have 3, you have 4, all the way up to positive infinity. And that is basically called that is called an infinite set, because the number of the elements of the set is not known, so it's an innumerable number of elements, so it's been called an infinite set. Now I'm just trying to give you as much detail as I can, but this is I'm just improvising. I'm not reading off any text or anything, so this is called an infinite set. Now this is a set that basically sets have this notation over here, and then you can give it a name. For example, you can call it the set of natural numbers, and for the set of natural numbers we happen to use the letter n, and these are all the counting numbers that we have come up with a long time ago, like even longer than probably 6,000 years ago. So for example, this, you could think of this as a set, or then you can take a portion of this set. You can take a portion of this set, for example 1, 2, 3 and 4, and out of these 4 elements you can create a new set and call it, for example, A, and that is again another set, but then this set is called a finite set, because you know how many elements there are in this set. There are 4 elements in this set. Now so basically what that is what a set is, and then there is different kinds of representations of a set. There is one we have representing a set called first of all there is the Venn diagram, then there is the I don't remember the names, okay, but wherever it's necessary we will get them, don't worry about that. What I want to do here is just familiarize you with the idea of a function. Now, of course, a set can contain anything. It can contain, for example, the name of the alphabets of the English language. It can contain, for example, the name of, for example, 5 objects. It can contain, for example, the name of 5 people. It can be anything. For example, B can be the set of, for example, the names Susan, for example, Rahul, I don't know, John, for example, and David, for example, and give me another name. I don't know, Beth, for example. Right? So a set can contain anything. For example, the name of people. So this is also a set. Now suppose that A is a set of two colors. Suppose that you have a set A over here, and that is basically basically two colors, for example, red and blue. And suppose that you have another set basically called B, which is basically three objects, for example B, C, and S. For example, you could go for example, you could go for example pants. For example, for pants and shirts and for example socks, right? And you could take P, S, and I don't know, T-shirt, for example. Take this as a T-shirt, and then you would have P, T, and S, for example. So I'm going to go with basically the set B. I'm going to take the first letters of the name of these objects and call them P, for example, T, and S. Now, if you want to figure out, or let me actually do it the same, in the exact same way that they have done it over here. They have represented basically a bag, a coat, and a shirt. And for a bag, they have taken a B. For a coat, they have taken a C. For a shirt, they have taken an S. So then your set B is going to be B, C, and S. B, C, and S. Now, the question is, how many pairs of colored objects can be made from these two sets? How many pairs of colored objects can be made from these two sets? And the answer is basically based on, there was something called I don't remember the name there either, but it's something along the lines, the fundamental rule of multiplication or something like that. So if you want to calculate all of the different colored objects that can be made from these two sets, you just simply multiply the number of colors here by the number of objects over here. 2 times 3 is equal to 6. That means that you can have basically a red bag, basically. So that would be a red bag. You could have a red coat. You could have a red coat. You could have a red, basically red shirt, or red S, basically. You could have a blue bag. You could have a blue bag. You could have a blue coat. You could have a blue coat, and you could have a blue shirt. So as you can see, the number of colored objects made from these two sets is 1, 2, 3, 4, 5, and 6. So basically what we get is six distinct objects. 6 distinct objects. So in the earlier classes, it seems that an ordered pair of elements, taken from any two sets P and Q, P and Q, is a pair of elements written in small brackets, and grouped together in a particular order, in a particular order. That is, basically we write this as P comma Q, and we write them in small brackets, where P basically belongs to the set P and Q belongs to the set Q. And this seems to, based on what I read over here, this seems to lead us to a definition. This seems to lead us to a definition called definition 1 here. Definition 1, which is given two non-empty sets P and Q, given two non-empty sets P and Q, the Cartesian product P times Q, the Cartesian product P times Q, meaning that P basically being the name of the set P and Q being the name of the set Q, is the set of all ordered pairs, of elements from P and Q. So basically, the given two non-empty sets P and Q, the Cartesian product P times Q is the set of all ordered pairs of elements from P and Q. That means that you can write P times Q, or the Cartesian product of these two sets, is basically a set which you can write as P comma Q, such that P belongs to P, and, or instead of and, you can also use a comma, and Q belongs to Q. Okay, so that is basically, that is called the Cartesian product of two sets P and Q, which is denoted by P times Q. So then from the illustration that we had about the two colors and the three objects, then you can write basically the colors were red and blue. So the set A was basically red and blue, and the objects were basically it was a bag, a coat, and a shirt. A bag, a coat, and a shirt. A bag, a coat, and a shirt. So then, and we got 6 distinct objects when we basically put these two sets together in that order. Basically, we said that we could have a red bag, a red coat, a red shirt. We could have a blue bag, a blue coat, and a blue shirt. So then the Cartesian product of A and B is going to be red, comma B, red, comma C, red, comma C, and red, comma S, and then blue, comma B, blue, comma C, and then blue, comma S. That is the Cartesian product of these two sets. And as you can see, all of these objects that you can see here are actually distinct objects, meaning that for example, I could take these are basically distinct objects. Now you need to pay attention to all of these points over here in order to understand what a function actually is, because a function is basically based on all of this discussion that we have here. Now there is of course something, and you of course based on this you I mean intuitively you understand that if either P or Q is a null set is basically a set that contains nothing. It's called a null set. So if basically either P or Q is a null set, then the Cartesian product of P and Q will also be an empty set. Will also be an empty set. An empty set. That means that is the Cartesian product of P and Q. That means the Cartesian product of P and Q will be equal to the null set is basically denoted by the Greek letter phi. So P times Q is going to be equal to phi. Phi is basically the notation that is used for the null set basically in the whole discussion of sets basically. Now there is basically one more thing that we need to talk about here, and that is basically we have two more sets here. Let's take a look at this example as well. This is the kind of example that will lead us into other parts of this discussion. Okay, so now there is basically another example over here that is about license plate of a car. It's related to three different basically states in India. So there is a set over here which has been called set A, and DL stands for Delhi. DL stands for Delhi. So that is basically one state in India. Then there is the MP, which is the Madhya Pradesh state in India, and there is another state, Karnataka, in India. Okay, so these are three different states: Delhi, Madhya Pradesh, and Karnataka, denoted by DL, MP, and KA. Now there is three numbers here. There is three two-digit numbers, 01, 02, and 03, that representing codes for the license plates of vehicles issued by these states. Meaning that each of these states is allowed to use any of these basically codes. Any state is allowed to use 03, 02, or 01, 02, or 03 for their license plates. And of course the combination of for example, let's say DL and for example 01 would be one license plate. Of course one probably a part of a license plate, and then they would give they would probably use, for example, a three-digit number as well, in order to make a complete license plate, for example, for each car, something like that. And so each of these states is allowed to use any of these codes. Now, as you can imagine, now if the three states, Delhi, Madhya Pradesh, and Karnataka, were making codes for the license plates of vehicles, with the restriction that the code begins with an element from the set A, with the restriction that, so this is the kind of condition that we have here, that the code begins with an element from set A, which are the pairs. Then what would be the pairs available from these sets, and how many such pairs would there be? So the question is, if there was the restriction that the code was to begin with an element from set A, and then each element of set A could be paired with each of the elements of set B, then which are the pairs available from these sets, and how many such pairs will be there. So then the available pairs in this situation would, for example, be DL, for example, 01, DL, for example, DL, 02, DL, 03, and then you have MP01, then you have MP02, and then you have MP03, and then you have MP03, then you have Karnataka or KA01, you have Karnataka 02, and then you have Karnataka 0,03, and you have Karnataka 03. So, and the product of set A and set B is given by, and so basically in this situation, the product of the Cartesian product of set A and set B is given by all of these elements in just one set like this. is just in just one set, meaning that the Cartesian product of all of these, of the two sets, would be basically this set over here. And the set, as you can see, has 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 3 times 3 is equal to 9. Okay, so basically now you can see that we have basically 9 such pairs of basically the state name and the code coming after the state name, and you get basically 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs of such basically combinations of codes, and also basically the order in which they appear. The order does indeed matter, meaning that the order matters, because, for example, suppose that this pair over here, for example, you have DL, 0, 1. So DL, 0, 1 is of course different from 0, 1, DL. So the order in which you choose the two different elements are going to be different, meaning that if you write DL, 0, 1 would be different from 0, 1, DL. Okay. Now you need to pay attention to all of the points that I point out to here, because these ultimately give you a very good understanding of functions in mathematics. So as another illustration, let us do another experiment. So let's say that you have two sets, A1 and A2. You have these two sets, for example, let's call it A is equal to basically A1, A2, and B as B1 through B4, and the set B as B1, B2, B3, and B4. So now A times B would be basically the set of all of these ordered pairs. For example, A1, B1, A1, B2. Now A1, B3, and A1, B4, and then you have basically A2, B1. You have A2, B2, B2, and A2, B3, B3, and A2, B4, B4. So that is basically all the ordered pairs that you get in this situation: 1, 2, 3, 4, 5, 6, and 7, which is not right. A1, B1, A1, B2, A1, B3, A1, B4, A2, B1, A2, B2, A2, B3, A2, B4. 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs, 2 times 4. Now, what they have done over here, they have said that the 8 ordered pairs thus formed can represent the position of points in the plane if A and B are subsets of the set of real numbers, and it is obvious that the point in position A1, B2 will be distinct from the point in the position A2, B1. So So I repeat this. It says that the 8 ordered pairs thus formed can represent the position of points in the plane. So these can represent the position of points, the position of points in the plane, if A and B, the sets A and B are subsets of the set of real numbers, and it is obvious that the point, and of course you can take this as, for example, this point, you can take it as A1 and, for example, A2, A1 and A2, and then you would have, for example, B1, B2, B3, B4. They have written this like this. Let me rearrange these points so that we can see something here. So they have taken this way, and then you have A1 and A2 over here, and then you can draw this line over here and connect these lines at these junctions. That's they have represented these points. For example, this point would be A1B, this point would be A1B1, this point would be A1B2, this point would be A1B3, and so on. And so, for example, this point would be A2B3. They have represented this like this. But more importantly, that what they're saying is that basically these 8 ordered pairs, these can represent the position of points in the plane if A and B are subsets of the set of real numbers. And of course, logically you know that the point in position A1, B2, for example, A1, B2 would be this point over here. The position of this point would be distinct from the position of the point B2, A1. B2, A1 would be basically, well, of course, some other point if you took this in the other way around. For example, B1, B2, A1 would be, for example, probably, of course, you would have to change the whole thing. But of course A1, B2 would be different from B2, A1, meaning that the order here does actually matter. Although, for example, in these 2 ordered pairs we are actually dealing only with A1 and B2, but the order is different. Now, there are a couple of remarks over here. Now, 2 ordered pairs are equal. Now, 2 ordered pairs are equal if and only if, which is IFF, the corresponding first elements are equal and the second elements are also equal. Meaning that if you have, for example, A, B and C, D, A, B is equal to C, D, if and only if A is equal to B and B is equal to D. So then you can say that 2 ordered pairs are equal if and only if the corresponding 2 first elements are are equal, and the correspondence and the second corresponding elements are equal. And moreover, if there are p elements in A and q elements in B, if there are p elements in A, and q elements in B, then there will be p times q elements in A times B. Then there will be p times q elements in A times B, or the Cartesian product of the two sets. That is n of A. That is, if n of A is equal to p, and n of B is equal to q, then n of A times, or the n of the Cartesian product of the two sets, is going to be p times q. So that is that. And if A and B are non-empty sets, and either A or B is an infinite set, then so is A times B. So if basically if A is not equal to if A or B are non-empty sets not equal to phi, and either A or B is an infinite set, then so is A times B, because one of them is going to be infinite set. And then there is one more remark here, that is basically that the Cartesian product of three sets A times A times A times A times A times A is equal to the set of basically triplets A, B, C, such that A, B, and C belong to A. And of course here A, B, C is called an ordered triplet. Okay. So that is that. That is basically that. Okay, so now let's basically, now what we need to do is basically I will end this video here, and then we will continue this discussion in probably a few more videos. We have still we will do a couple of examples from here, and then we will get into the discussion of a relation, see what a relation is, and then we will get into the discussion of a function, and then I will show you some functions, their domain and their range and their codomain and things like that. So I will see you in the next one. I think we are going to need a couple of videos here in order to finish this chapter. It's not a lot of material, but it's what is required here in order to understand the rest of the material. So I'll see you in the next video. Thank you.